Hello everyone. Today we are discussing about particle accelerators. And my name is Kusmanvita, roll number 123EC 0052. Particle accelerator. First, particle accelerators means a particle accelerator is a machine that uses electromagnetic fields to propel charged particles such as protons or electrons to very high speeds and direct them into a control beam. Simply, a particle accelerator means to study the fundamental properties of energy and matter by causing collisions. The largest accelerators are used in research on the fundamental interactions of the elementary subatomic particles. Principles of particle acceleration. Particle accelerators exist in many shapes and sizes. But the smallest accelerators share common elements with the larger devices. All accelerators must have electric field to accelerate the particles and they must have magnetic fields to control the paths of the particles. Also, the particles must travel through a good vacuum, that is, in a container with as little residual air as possible as in a television tube. Generating particles. Electrons and protons, the particles most commonly used in accelerators, are found in all materials, but for an accelerator, the appropriate particles must be separated out. Electrons are usually produced in exactly the same way as in a television picture tube, in a device known as electron gun. The gun contains a cathode in a vacuum which is heated so that electrons break away from the atoms in the cathode material. As with electrons, there are protons in all materials, but only the nuclei of hydrogen atoms consist of a single protons. So hydrogen gas is the source of particles for proton accelerators. In this case, the gas is ionized, the electrons and protons are separated in an electric field, and the protons escape to a hole. They are later passed through thin foils to strip off the electrons before the protons move to the final stage of acceleration. Accelerating particles. The key feature of any particle accelerator is the accelerating electric field. The simplest example is a uniform static field between positive and negative electric potentials, much like the field that exists between the terminals of an electric battery. The difference in electric potential between the position where the electron begins moving through the field and the place where it leaves the field determines the energy that the electrons acquires. This is a tiny amount of energy equivalent to 1.6 into 10 to the power of minus 19 joule. A flying mosquito has about a trillion times this energy. However, in a television tube, electrons are accelerated through more than 10,000 volts, giving them energy above 10,000 electron volts or 10 kilo electron volts. Many particle accelerators reach much higher energy measured in mega electron volts, giga electron volts, or tetra electron volts. History about particle accelerators. Most of the development of particle accelerator has been motivated by research into the properties of atomic nuclei and subatomic particles. Starting with British physicist Ernest Rutherford's discovery in 1919 of a reaction between a nitrogen nucleus and an alpha particle. All research in nuclear physics until 1932 was performed with alpha particles released by the decay of naturally radioactive elements. Natural alpha particles have kinetic energy as high as 8 megaelectronvolts. But Rutherford believed that in order to observe the disintegration of heavier nuclei by alpha particles, it would be necessary to accelerate alpha ion artificially to even higher energies. Other developments of the period demonstrated principles still employed in the design of particle accelerator. The first successful experiments with artificially accelerated ions were performed in England at University by Cambridge by John Douglas Cockcroft and E.T.S. Walton in 1932. And at Princeton University in New Jersey, Robert J. Van de Graaff has constructed the first built-charge electrostatic high-voltage generator. According to previous history, the principle of the linear resonance accelerator was demonstrated by Rolf White-Wall in 1928 at the Rhenish-Westphalian Technical University in Aachen, while Roy used alternating high voltage to accelerate ions of sodium and potassium to energies twice as high as those imparted by one application of the peak voltage. In 1931, in the United States, Lawrence and his assistant David H. Sloan at the University of California, Berkeley, employed high-frequency fields to accelerate mercury ions to more than 1.2 megaelectrons. And in 1931, Lawrence's student M.S. Livingston demonstrated the principle of the cyclotron, producing 80 kiloelectronvolts ions. In 1932, Lawrence and Livingston announced the acceleration of protons to more than 1 megaelectronvolt. Later in 1930s, cyclotron energies reached about 25 megaelectronvolts and Van de Graaff generators about 4 megaelectronvolts. In 1940, Donald Quiz, applying the results of careful orbit calculations to the design of magnets, constructed the first Beavatron, a magnetic induction accelerator of electrons at the University of Illinois. Constant voltage accelerator. The simplest type of particle accelerator is constructed by mounting a particle source on one end of an insulated evacuated tube and creating a high voltage between the ends with the polarity such that the particles are impelled from the source toward the far end of the tube. Even more difficult to control are sparks within the equipment and in positive ion accelerator. Unwanted secondary beams produced when the accelerated ions strike the end of cyclotrons. The magnetic resonance accelerator or cyclotron was the first cyclic accelerator and the first resonant accelerator that produced particles energetic enough to be useful for nuclear research. More than 1200 cyclotrons around the world create proton or deuteron beams for medical uses. Classical cyclotrons. The key to the operation of cyclotron is the fact that the orbits of ions in a uniform magnetic field are isochronous, that is, the time taken by a particle of a given mass to make one complete circuit is the same at any speed or energy as long as the speed is much less than that of light. In some consequences, of a slight weakening of the magnetic field toward the peripheries of the Ds, as in the Beavatron. The energy gained by a particle in a classical cyclotron is limited by the realistic increase in the mass of the particle, a phenomenon that causes the orbital frequency to decrease and the particles to get out of phase with the alternating voltage. The beam current in a classical cyclotron operated at high voltages can be as high as 5 milliamperes. Intensities of this magnitude are very useful in the synthesis of radioisotopes. And this was a cyclotron diagram where vacuum chamber, magnetic field, these ion source, electric field region, beam, target. These are the main synthesis points in classic synchrocyclotrons. Cyclotrons in which the frequency of the accelerating voltage is changed as the particles are accelerated are called synchrocyclotrons. Frequency modulated cyclotrons are plastrons. Moreover, the magnetic focusing can be made stronger so that the magnetic field need not be so precisely happen. And this was the figure of synchrocyclotron. How about we are up to the conclusion? To understand the particle accelerated in the below diagram is helpful, and it was defined in different statements and different applications. It became essential tools in both understanding the universe at its most fundamental level. Some of the applications must be derived is ion implanters, electron beam accelerator, Linux, cyclotrons, synchrotrons, electrostatic accelerators. These are defined by this one. Thank you.